Okay, so if you missed the lesson, this is what we're talking about today. We're talking about dilations. And yes, dilations are another form of a transformation. So they kind of go in the family of reflections, translations, and rotations. Remember those? Those preserve distance. So do you think a dilation preserves distance? No, because you know a dilation changes size. So what's that good catchphrase I want you to realize? I want you to remember that dilations preserve angle measure. They do not preserve distance. Dilations only preserve angle measure. So that means that a dilation creates a similar triangle or similar figures. You learn that reflections, rotations, and translations created congruent figures. Dilations create similar figures because dilations preserve angle measure, and similar triangles have congruent angles. So that looks pretty good. So let's practice some dilations. So we have some triangle. We're going to call it triangle CFT. So let's draw a picture of what triangle CFT might look like. I don't know, maybe it looks like that. Here's C, here's F, here's T. That one's not going to work for me, so I'm going to switch these two letters real quick. I'm going to draw a new triangle. You'll see why in a minute. Here's C, here's F, here's T. I know the measure of angle F is 40, so I'm going to put a little 40 there. And also the length of FT is 8. Now watch what goes on. Here's our verbiage we want to use. A dilation has a scale factor. It's what we multiply to enlarge or diminish the sides. It's how we change the sides. So it's a scale factor of 2. And it has a center. In this case, it's centered at vertex C. So what's happening is I need to multiply the side lengths by a scale factor of 2. So I'm basically taking the distance from C to F that I'm drawing here in green, and I'm going to basically double that distance. That looks about right. So here's where a point F prime is. And likewise, I'm going to double the distance from point C. So maybe T looks like it's about down there, T prime. And then I'm going to draw in that other side there. So notice now that triangle C, F prime, T prime is a dilation of 2 of triangle CFT. And the center of our dilation is point C. So we just saw that dilations are not rigid motions. So they create similar figures. They don't preserve distance, they only preserve angle. So the measure of angle F prime is going to be 40 degrees. Because those two angles will be the same. It's just a dilation. It doesn't change the size of the angle. But it does change the measure of F prime T prime. A scale factor of 2 is going to double that measurement to 16. So that's our idea behind our dilations. We make a similar triangle. The angles are congruent, but we've just changed the side lengths. So I have two figures here. I have triangle man. Triangle man is the image of triangle boy after a dilation centered at Z. So notice that since triangle man is the image, we're doing something to triangle boy to get to triangle man. We're making the triangle larger. So if we want a ratio to represent the scale factor, that ratio has to be a ratio that's greater than 1. And here's what I like to do. I'm going to draw in line segment ZBM. Notice, and I'll even do this, let's draw in this one too, ZOA. Notice what's happening now is I'm taking the length of, let's see, we'll do it in green also. Let me draw a couple other things too. So basically, since man is the image of boy, I'm taking the length of ZB and I'm going to multiply it by some number to get to Zm. I'm increasing the distance from Z to B and making it from Z to M. And I have the same argument from ZO, making it larger to go to ZA. So a ratio that could represent the scale factor. Because I need to get bigger, I need the bigger measure on top. So maybe one ratio is the length Zm to Zb. An equivalent one, you might say, would be Za to Zo. Again, because it has to be bigger, I need to make this fraction larger than 1. And since Zm is greater than Zb, the value of that fraction is going to be greater than 1. So those are two other ones. Do you want to also do like Zn to Zy? You could do that too. Let's go the other way. Okay, same kind of diagram, but now boy is the image of man. So now we're starting at triangle man, and we're going to triangle boy. So if I think of it the same way as I did before, I'm taking that length of a segment, and I'm going to shrink it. I'm going to make it smaller, and it's going to be that segment there. Or again, if we want to go to the other one, if we want to go from ZA down to ZO, we could do that. So again, now because we're going from a larger to a smaller, our scale factor has to be less than 1. So less than 1 might be ZB to ZM. Or another one could be ZO to ZA. So notice from here, if we're making the figure smaller, our ratio, our scale factor has to be less than 1. If we're making it larger, like the previous one, the scale factors would be greater than 1 when we put the bigger measure on top. Okay, so if you have your grid paper handy, we're given point A and point B, and we'll even draw in segment AB. There's segment AB. I want to make a graph of A prime, B prime, the image of this segment, after a dilation of 3 that is centered at point D. So from point D, I'm doing a scale factor of 3. So if we treat the distance from D to A as a scale factor of 1, think about that for a minute. If you multiply something by 1, do you change its size? No, you don't. So a dilation of 1 just brings it right to itself. But notice that what I did was I kind of went down 3, and then I went to the left 1. I went down 3, left 1 to get to A. And that's one length, one distance. So I got to do this 3 times to get to a scale factor of 3. So there's 1. If I go down 3 over 1, there's 2. Down 3 over 1. So here's where a point A prime is going to be. It's a dilation of 3. And if you take a look at the distance here, that blue distance compared to this green distance, the green distance is 3 times as big as the blue distance. So doing the same thing for D to B, it looks like we're going down 4 and over 2. So let's go down 4 and over 2 once, down 4 and over 2 twice. Here's where B prime is going to be. So again, that distance that we go there, I want to go 3 times its distance. So for my final answer, when I graph A prime, B prime, and I draw the segment, that segment is my answer right there. So now you can dilate a segment by its scale factor. And the nice way to do that, like you see here, is you just kind of count the distances. Well, let's go the other way now. Suppose you're given a triangle, triangle ABC, and then you have its image, triangle A prime, B prime, C prime. I want to determine what transformation. So when I read transformation, I think reflection, rotation, translation. It's none of those. Dilation, yeah, the size changed. So my answer is going to be a dilation. But a dilation needs two things. It needs the center of dilation, and then it needs the scale factor. I need those two things. So first I identify that it's a dilation. Well, here's a nice way to find the center. If you notice, I'm going to go back a little bit. I'm going to go back to here. If you notice how we drew these green and blue segments that joined a point, like a vertex to another vertex, and the dilation center, point Z, was on those segments, I'm basically going to find point Z here. So I'm going to go from A prime. It looks like I go right 3, down 1 to A. Let me keep going, right 3, down 1, right 3, down 1. The center of dilation is going to lie on that red segment. Let's do the same thing from B prime down to B. It looks like I'm going down 4 over 1, down 4 over 1. It looks like I'm hitting right at the origin. Okay, let's just check it with point C prime to C. It looks like I'm going up 3, left 3, so let's go up another 3, left 3. Look at that. There's my center of dilation. So the center of dilation in this case is the point 0, 0. You want to call it the origin. I'm good with that too. Cool. Now let's determine our scale factor. From the origin, to go from the origin to point A, it looks like we went left 3 and up 1. Well, if we do another left 3 and up 1, we get to A prime. So we've done 2 left 3 and up 1s. So our scale factor is 2. So if you're given a figure and its image, use this process to determine the scale factor and the center of the dilation. Okay, I want to go back to something. I want to go back to what we did before. Remember we took segment AB and we dilated it to get segment A prime, B prime? I want you to notice something here. Basically, when you dilated from point D to point A, I think you kind of knew that point A prime was going to lie somewhere on that green line. And the same with this red line here. You can kind of tell that point B prime was going to lie on that red line. But take a look at the line that contains segment AB. It kind of looks like this line here. Notice that the image is not the same line. The image is actually a parallel line. How do you know it's parallel? Well, the slopes are the same. Remember that? Remember parallel lines have the same slope? So here's what I'm thinking about in terms of our dilations. When you do a dilation, you want to take a look at that center point. Because if the center point is on the line, notice my center point, my point D, was on my green line. So that meant when I dilated segment AD, it stayed on the line. So really, the line that included AD didn't change. And the same with the red line. When you dilate a point and the center of dilation is on the line, the point just moves further down the line. So the green line and the red line remain unchanged. But the blue line, notice that the center of dilation is not on the blue line. My point D is not on line AB. So therefore, the new line is a parallel line. That's a pretty cool math rule here. Oh, I went too far. This is definitely a conjecture worth writing down. I can just about guarantee this is a Regents question, and this is question number 2 on your test next week. A dilation takes a line not passing through the center of dilation to a parallel line. That was the blue line. And it leaves a line passing through the center unchanged. That's the red line, and that's the green line. A dilation takes a line not passing through the center of dilation to a parallel line. and leaves the line passing through it unchanged. Pause the video for a second. Okay, if you got all that down, take a look at what we did. We just said that because the blue line does not contain the center of dilation, it moves to a parallel line. The green line and the red line contain the center of dilation. Those lines don't change under a dilation. That's what that rule says. All right, so let me talk about the question I'm going to ask you on your test, and most likely will appear in your Regents exam. These are on the exam all the time. So you got an equation of a line, and the line is dilated by a scale factor of 2 centered at 1, 2. So we want to know an image of this line. What would be the image of the dilation? Well, the first question I got to figure out, is this point on the line? That's my question. Is the point on the line? How do we test that? Plug in x and y. So I want to see, is 3 times 1 plus 2 times 2, does that equal 6? Nah, it equals 7, right? 3 times 1 is 3, 2 times 2 is 4. So it does not equal 6. So that means that point is not on the line. So that means it goes to a parallel line. So let's figure out that line parallel to it. So I'm first going to take my equation 3x plus 2y equals 6. And I'm going to put it in that y equals form. Because the y equals form is easier to make parallel lines with. So first of all, let's see, we're going to subtract 3x. Here's a little bit of algebra for you. I get 2y equals negative 3x plus 6. Divide everything by 2. So this equation is y equals negative 3/2 x plus 3. Okay, that's not my answer. Stop. So now I want to dilate this line. So dilate with a scale factor of 2. When I dilate it by a scale factor of 2, the slope stays the same because the lines are parallel. So it's going to say y equals negative 3/2 x, still going to be that. But the y-intercept is what's going to change. So on my y-intercept right now is 3. I'm going to multiply that by 2 and get 6. The scale factor is 2, so I multiply the 3 and the 2 to get 6. So this is the equation of the dilated line. This is the answer we're looking for. So the process, take a look. Is the point on the line? If it isn't, come up with the parallel line. Let's take a look at one more of these. I have 4x minus 3y equals 6. A dilation of scale factor 3. The center's at 0, negative 2. My first question, is that point on the line? Let's figure it out. Plug it in, plug it in. I get 4 times 0, negative 3 times negative 2. Check it out. This is a true statement. It is. So that means the line's equation doesn't change. The line's equation then is unchanged. So the answer is just going to be 4x minus 3y equals 6. We don't change it. If the point wasn't on the line, we'd have to do the dilation. But if the point is on the line, you're done with the problem. And guess what? We're done with the lesson. You guys did so good. Take a look at the practice worksheet there, the answers to it on Google Classroom. Remember, you are responsible for the work that you miss. So thank you for watching this video. Thank you for practicing, and good luck on the worksheet and on the test.